primarily graphing simultaneous inequalities. You have several inequalities and you want to graph them all at the same time on the same graph. The application is going to be a branch of operations research called linear programming. Quite often a corporation is in the following situation. They have multiple products that they are offering for sale. The selling price of each product may be slightly different, and the market demand for each product may be slightly different. So for example, an electronics company could be manufacturing several different models of a tablet PC, and they have a choice of how many of each model to offer. And of course they're in business to make money, and so they would like to maximize their profit. Meanwhile, they probably have some constraints. Every company, in fact, has constraints. They may be able to only afford to hire a certain number of employees, or they may be limited on their factory floor space to only be able to install a certain number of manufacturing equipment items. Or they may be under legal constrictions. The laws may restrict how much pollution they're able to emit, or some other consideration like this. So the overall goal then is, given the constraints that we have, decide which mixture of products to make in order to maximize our profit. In real life, these problems can be huge and very, very complicated. Let's look at a very simplified example here to start out with. I'll just read the example. Suppose, and it's from the point of view of a bakery, suppose a fruit pastry can be made from 3 ounces of fruit and 2 ounces of dough, while a pie requires 13 ounces of fruit and 7 ounces of dough. Suppose also the bakery has 5,000 ounces of fruit and 2,000 ounces of dough available, and that it can sell all the baked goods it makes at a profit of 50 cents per pastry and $4 per pie. The bakery wants to know how many of each it should make to maximize its profit. Write down algebraic expressions to mathematically represent the objective and constraints of the problem. In this first example, we're just going to set up the mathematical problem and not actually solve it. Later on, we'll discuss the solution technique. Let's start by filling out this chart. Along the rows here, I've listed products, and that is the output. That is what this particular company, is producing. In this case, the problem said we can make pastries or we can make pies. For column headers, I've listed resources, or in this case, ingredients might be a more common word. These are your inputs. This is what you have to work with. And the problem mentions that we have a certain amount of fruit available to be used and a certain amount of dough. These are both measured in ounces. Regarding the products that are made, there is a profit mentioned for each of them. And regarding the resources that we use, there's a maximum available amount for usage that's mentioned. Ultimately, the bakery wants to know how many of each product it should make to maximize its profit. In mathematics, it's very often the case that you want to introduce variables for the quantities that you're trying to find. And so let's do that. Let's let x be number of pastries and y be number of pies, and our goal in mathematical language then is to find x and y. Now let's go ahead and see if we can fill out the rest of the table. These are resources per unit of product. So for example, for each pastry I require a certain amount of fruit. That's specifically said in the very first sentence here. A pastry can be made from 3 ounces of fruit. Also, a pastry requires 2 ounces of dough. On the other hand, a pie requires 13 ounces of fruit and 7 ounces of dough. That's the content of the first sentence. The second sentence says that the bakery has 5,000 ounces of fruit and 2,000 ounces of dough available. So 5,000 ounces of fruit, 2,000 ounces of dough available. And finally, there's a part of a sentence that says the bakery can sell all the goods it makes at a profit of 50 cents per pastry. I'll work in units of dollars here, so 0.5, and $4 per pie. So we really haven't done anything except take the numbers that are given in the English sentences of the original question and put them into an organized table. Now, let's translate that into algebraic expressions that will provide a mathematical problem then to solve. Objective function refers to what we're trying to do. First of all, this problem deals with profit, and of course we want to maximize profit. We then would like an expression for that profit. So what is profit? Well, if I look back here, I'm making $0.50 per pastry that I make. So 50 cents per pastry that I make. So if I make 2 pastries, I make 50 cents times 2. If I make 10 pastries, I make 50 cents times 10, and so on. So if I make X pastries, and right now I don't know what X is, so we actually will use the letter. If I make X pastries, then the profit from making pastries is going to be 0.5x. Let me just add a note. This is profit from making pastries. We're also making pies, and pies sell for more, and we make more money per pie, specifically $4 per pie. So if I make Y pies at $4 per pie, that's plus 4Y, and this is profit from pies. If I add the two profits together, all the profit I make from selling pastries plus all the profit I make from selling pies, that's my total profit. And so I want to choose X and Y in order to make P be as big of a number as possible. But there are constraints involved. I only have a certain amount of fruit available and a certain amount of dough available. Regarding the fruit, first of all, it takes 3 ounces of fruit to make each pastry. And so similar to how we handled the profit, if I make, say, 5 pastries at 3 ounces of fruit per pastry, that's 3 times 5 ounces of fruit that I will use. So if I make X pastries in the general case at 3 ounces of fruit per pastry, I'm going to use 3x ounces of fruit in making pastries. Then I'm also going to use some fruit in making pies, 13 ounces per pie times Y pies, so 13Y. And we have 5,000 ounces of fruit available. Of course, I don't have to use it all. It's fine to have some left over. I can save it for later or throw it away or whatever. But it's not okay to go more than 5,000. That's simply not available for whatever reason. That's an inequality. This expression needs to be less than or equal to 5,000. This is fruit used for pastries, and this is fruit used for pies. There's also a limited amount of dough available, 2,000 ounces. So if I use 2 ounces of dough per pastry and 7 ounces of dough per pie, I'll come up with a mathematical expression that 2 times x plus 7 times y needs to be less than or equal to 2,000. So similarly, this is dough used for pastries, and the 7y is dough used for pies. So again, our goal is to choose x and y so that profit is as large as possible, but I can't just choose any x and y that I want. The x's and y's that I choose have to obey these two inequalities when I plug in for x and y in the expressions. There's one more thing to point out. X and Y are physical variables. They have physical meanings. They are the number of pastries and number of pies, respectively. And those numbers have to be non-negative quantities. I can't make negative 17 pies or negative 35 pastries. So I also, for physical reality, need X to be greater than or equal to 0 and Y to be greater than or equal to 0. Those are called minimum constraints. They're just there to express physical reality. These up here are called resource constraints. They express the fact that I only have a limited amount of each resource available. And so that's the setup. Maximize profit by choosing X and Y that obey all 4 inequalities now. Let's set up one more example before we go on to talk about the solution technique. You may want to pause the video and try to work this one out on your own first. And it looks like this. I'll go ahead and construct a resource table similar to what we had before. This is not absolutely necessary, and after you've done a few of these, you might find yourself just skipping this step and going and writing down the linear programming problem directly, the inequalities directly. But for now, I'll go ahead and construct a table similar to what we had before. So actually, I think this is basically the structure that we had. Products went here, resources went here, and here was profit before. So let's look at this question. A trucking firm ships containers for 2 companies, Anton and Bell, the names of the 2 companies. The containers from Anton weigh 40 pounds each and are 2 cubic feet in volume. The containers from Bell weigh 50 pounds each and are 3 cubic feet in volume. Anton will pay $2.50 for each container shipped. Bell will pay $3 per container. The firm's trucks can only carry loads that are at most 37,000 pounds and 2,000 cubic feet. The trucking firm wants to know how many containers from each company should be placed on each truck to maximize the firm's income. Again, just set up the problem. We'll talk about solution later. So we need to decide on our products. What are we producing here? This time the products are not physical objects like pies and pastries. They are, in some sense, they are shipping objects. So they are the number of Anton containers and the number of Bell containers. So let's let A be number containers of Anton and B be the number of containers of Bell products that are shipped. So we're not actually making these, but we are shipping them. In terms of constraints, there's a sentence here: the firm's trucks can only carry loads that are at most 37,000 pounds and 2,000 cubic feet. If you think about packing a semi-trailer, There's a weight limit. You're not allowed to carry as heavy a load as you want because it's hard on the roads. And there's also obviously a volume constraint. A shipping container only holds a certain number of cubic feet. So one of the constraints is how much weight we can put in. Let's let that be in pounds. The other is how much volume is taken up by what we're shipping. And the units that are mentioned there for the problem are cubic feet. Finally, the goal of the problem is to decide how many containers from each company should be placed on each truck to maximize the firm's income. So in this case, we're trying to maximize income. And if we go ahead and there's a certain amount of each resource available. If we go ahead and read through, the containers from Anton weigh 40 pounds each and are 2 cubic feet in volume, while the containers from Bell weigh 50 pounds each and are 3 cubic feet in volume. Anton will pay $2.50 for each container shipped. So in other words, our income from shipping an Anton container is $2.5. And Bell will pay $3 per container shipped. The firm's trucks can only carry up to 37,000 pounds and up to 2,000 cubic feet. So now we've converted the English text into tabular form, and our goal is to maximize income. What is that? Income equals, we're going to make income from Anton containers and some income from Bell containers. From Anton containers, $2.5 per container times the number of Anton containers. Add that to the income from shipping Bell containers, $3 per container times the number of Bell containers shipped. Maximize that income subject to some constraints. We'll have a constraint on weight. That is that 40 pounds per Anton container times the number of Anton containers. This is the total weight of the Anton containers that we load, plus 50 pounds per Bell container times the number of Bell containers. So the second term is the amount of weight, the total weight of the Bell containers we're shipping. That can't be any more than, so is less than or equal to 37,000. Notice that each term in this expression has a physical meaning. This is total weight of Anton containers shipped plus total weight of Bell containers shipped is less than or equal to 37,000. Each of the three terms in this inequality has units of pounds. There's also a volume constraint. That's 2 times A plus 3 times B is less than or equal to 2,000. And finally, there are minimum constraints. Again, A and B are physical quantities. They're numbers of containers, so we need A to be greater than or equal to 0, and also B to be greater than or equal to 0. And when we say set up the problem, set up the linear programming problem, here it is. This is the mathematical problem that we'll want to be able to solve now. Find A and B that maximize income subject to the constraints. All right, let's talk about solving those types of problems. First of all, there's something called a feasible region. That's the set of all points in the plane that satisfy all the constraints. If you remember from section 4.1, we were reviewing problems like this. I did one example at the end where there were 4 inequalities, and we found the set of all points that satisfy all 4 of those inequalities. In problems like this that are coming up, we also have multiple inequalities. So the set of all points that satisfy all inequalities in the problem are called that set is called the feasible region. Our goal then is to find the points in the feasible region that maximize the profit function. So in my first example, I had x's and y's standing for number of pastries and number of pies. And so x here could be number of pastries, y could be number of pies. My job is to choose the value of x and y that are in the feasible region. So it's a possible choice that the bakery could choose that give the maximum profit. Let's suppose, for the sake of discussion, that the profit function is given as 5x plus 2y. So now I want to show the general principle of how you go about looking for the best place in the feasible region to be. Question: what's the set of all points for which the profit equals $10? Okay, profit is 5x plus 2y. So the question is, what's the set of all points for which 5x plus 2y equals 10? What's the graph of that look like? Well, the answer is it's a line. In fact, it's a line. If we were to put it in slope-intercept form, y equals minus 5 halves x plus 5. Remember, this is the slope, the negative 5 halves. This is the y-intercept, the plus 5. And so it may be a line that looks, say, like this. 5x plus 2y equals 10. What's the set of all points for which the profit equals $20? Well, that's asking the question, what's the set of all points that satisfy the equation 5x plus 2y equals 20? Or in slope-intercept form, y equals negative 5 halves x plus 10. Notice that these two lines have exactly the same slope, but they have different y-intercepts. And so the green line that I'm about to draw needs to be, or will be, parallel to the red line. It might be something like this. 5x plus 2y equal 10. And of course, if I'm trying to maximize profit, it's better to, that's a 20, rather, right here is a 20. Of course, it's better to make $20 profit than $10 profit. So I can be anywhere in the feasible region. If I'm anywhere on the red line, I make $10 profit. If I'm anywhere on the green line, I make $20 profit. I'd rather make 20, so points on the green line are better than points on the red line. But then you say, well, okay, if it was better to move in this direction from the red line to the green line, then maybe it would be better to be over here somewhere, and over here somewhere. So instead of being on the green line, maybe it'd be better to be on an orange line. That may correspond to something like profit equals 25 or 30. So it always seems to be better in this situation to move up and to the right. That may be different in different problems, but for the profit function we're given here, moving up and to the right seems better. And so what you want to do is move up and to the right as far as you can, but remember you have to stay in the feasible region. So if you ask yourself, what happens if I move up and to the right as far as I can until I'm still just in the feasible region? And notice that would be a situation where you would end up on this line. This is the last such parallel line as I move up and to the right, which still touches the feasible region. Where does it touch the feasible region? Right here at a corner point. That's the key to this discussion. Where in the feasible region should we expect to find the maximum? At a corner point. I'll call that the corner point principle, say. And it also tells us how then to solve the problem. There are an infinite number of points in the feasible region. I couldn't possibly check the profit at each of those. But this particular feasible region only has 4 corner points. And so if I knew the profit at each of the corner points, and I knew that one of those corner points gave the maximum profit, I'd just compare those 4 profits and choose the biggest one. That's exactly the solution technique. So let's work an example. I want to maximize P equals 4x plus 5y, subject to x plus 2y less than or equal to 6, 5x plus 4y less than or equal to 20, and x and y both greater than or equal to 0. Since x and y are greater than or equal to 0, it makes sense to draw a graph where the first quadrant is used. And now if I graph the first inequality, remember our intercept-intercept form, the x-intercept is 6 and the y-intercept is 3. So here's 6, here's 3. This is the line x plus 2y less than equals 6. If I look at the other line, 5x plus 4y equals 20, the x-intercept is going to be 4 and the y-intercept is going to be 5. And that is the line 5x plus 4y equals 20. All right. X greater than or equal to 0, y greater than or equal to 0. Well, x equals 0 and y equals 0 are the coordinate axes. So you've seen similar pictures now before. If we go through with our check-a-point and see which side of the lines you want to be on, in particular for the black line, 0, 0, the origin works. 0 plus 2 times 0 is less than or equal to 6. So I want to be on this side of the black line. Check the origin for the second inequality. I want to be on this side of the red line. The other inequalities tell me I want to be on this side of the y-axis and this side of the x-axis. So the feasible region is out in here. It has 4 corner points. 1, 2, 3, and 4. And they have coordinates 0, 0, 4, 0, 0, 3, and here we would have to do some algebra. So if you were to solve x plus 2y equals 6 and 5x plus 4y equals 20, if you solve these two equations together, you'll find out that this point is 8/3, 5/3. That's just algebra. If you think you need to do it, go ahead and pause the video and do it on your own. So as we said, now I know that the maximum profit is achieved at one of these 4 corner points. Let's just check the profit at each of the corner points. So I'll make a table. XY is giving the coordinates of the corner points, and then P is 4x plus 5y. I'll list the corner points. They are 0, 0, 0, 3, 4, 0, and 8/3, 5/3. Okay, now what do? We take each of the corner point coordinates and plug it into the profit function. So for 0, 0, I want to evaluate 4 times 0 plus 5 times 0. And of course I get 0. If I don't make anything, I don't make any profit. Then there's 4 times 0 plus 5 times 3. That's 15. There's 4 times 4 plus 5 times 0. That's 16. And there's 4 times 8/3 plus 5 times 5/3, which works out to be, and if you do the addition of fractions, this turns out to be 19. 57/3. All right, I have my 4 choices for profit, P. I am looking to maximize, so here is the maximum. And let's conclude with just an English phrase of what we've discovered. The maximum profit is P equals 19. And how do you get that maximum profit? You let X and Y be 8/3 and 5/3 respectively. So choose X equals 8/3, Y equals 5/3 in order to get P equals 19, and that's the biggest value of P that you can get that obeys all of these constraints. Okay, let's look at a couple of other examples, putting everything together here. I'll just read the problem. A recycling company uses scrap cloth and scrap paper to make 2 different grades, A and B, of recycled paper. One batch of grade A requires 25 pounds of scrap cloth and 10 pounds of scrap paper, while one batch of grade B requires 10 pounds of scrap cloth and 20 pounds of scrap paper. The company has 100 pounds of scrap cloth and 120 pounds of scrap paper on hand. One batch of grade A paper brings a profit of $500, while one batch of grade B paper brings a profit of $250. How many batches of each grade should the company make to maximize profit? Let's work this from beginning to end, but I'm going to brush over some of the algebra steps in the middle. By now we've done quite a bit of graphing of lines and shading this correct side of the inequality and so on. So, okay, what do we want to know? How many batches of each grade should the company make? So maybe a good idea to let variables stand for those. I'm going to go directly to the linear programming problem without making the resource table like we did in the previous examples. Let's let X be the number of batches of grade A paper, and Y be the number of batches of grade B paper. Now, what do we want to do? Maximize profit. And what is that? Let's look at the dollar amounts. Each batch of grade A paper brings a profit of $500, grade B $250 each. So profit is 500X plus 250Y. Subject to constraints. We have scrap cloth and scrap paper to work with. So regarding the cloth, each batch of grade A requires 25 pounds. We have X batches, so 25X. Each batch of grade B requires 10 pounds, so plus 10. We have Y of those. And we can't use any more than 100 pounds of scrap cloth. And regarding scrap paper, each batch of A requires 10 pounds. Each batch of B requires 20 pounds. And we have a total of 120 pounds of that paper to work with. Finally, X and Y are numbers of batches, and so they need to be non-negative numbers. So as we do our graph, as is often the case, we'll put the coordinate axes so that we can do most of our graphing in the first quadrant where both variables are non-negative. All right, if we look at the equation that's associated with this inequality, the x-intercept is 4 and the y-intercept is 10. This was 25x plus 10y equals 100. And if we look at the second inequality, the x-intercept is 12 and the y-intercept is 6. And the red line is 10x plus 20y equals 120. All right, if we think about the shading, we want to go in this direction and this direction and this direction, and so the feasible region is here. Similar geometric situation to what we've seen on other examples, with 4 corner points: 0, 0, 0, 6, 4, 0. And here, if you solve the red and the black equations simultaneously, if you can show that this intersection point is 2, 5. So as we did in the previous example, now let's make a chart with the coordinates of each corner point and the value of the profit function at each of those coordinates. So our corner points are listed here. And 0, 0 plugged in here gives 0 profit. 4, 0 plugged in gives 2,000. 0, 6 plugged in gives 1,500. And 2, 5 plugged in gives 2,250. We're looking for the maximum. Of course, it's here. And so I'd like for you to answer an applied problem like this in an English sentence, or at least an English phrase. The maximum profit of $2,250 is made by making, and X was 2, and X was the number of batches of grade A paper, so making 2 batches of grade A, and Y was 5, that was the number of batches of grade B. And conclusion, that's the final answer to the question. Let's look at one more example. This one's a little more involved in terms of the number of constraints. It reads, a small group of monks decides to subsist on 2 foods, bread and milk. Suppose one slice of bread contains 1 gram of protein and 60 calories and costs 2 cents per slice. 1 cup of milk contains 9 grams of protein and 90 calories and costs 10 cents. To guard against excess, the monks, these are monks after all, so they don't eat much, decide to restrict their daily combined diet to at most 100 slices of bread and 40 cups of milk. Find the daily bread-milk diet that contains at least 90 grams of protein and 2,700 calories, such that the cost of the diet is a minimum. I should add that you're going to be doing another course project before long, and this problem is most closely related to the content of the second project. All right, let's list some things. I want to find the bread milk diet that contains a certain amount of protein and calories while minimizing cost. What do we have to decide here? The monks only have two foods, bread and milk, and so all we have to do is decide how much of each of those foods they should be eating. So let's let x be number of servings, which for bread it's slices of bread. And this, by the way, they're going to purchase for all of them. So by x, number of slices of bread that they're all going to eat together. And y is a measure of how much milk is going to be consumed, and the units for milk in this problem were cups. So y is number cups of milk, again, for all of them put together. What do we want to do? This time we want to minimize. Cost is a bad thing from our perspective. We want the smallest possible cost. And what is that? Well, bread costs 2 cents per slice. We have x slices of that. And milk costs 10 cents per cup, and we have y cups of that. So minimize 2x plus 10y, subject to. All right, what's involved here? We have to get a diet that contains enough protein. That's a health consideration. Won't do well without that. And so how about protein? Each slice of bread contains 1 gram of protein. So if we eat x slices, we'll have 1 times x, or just x grams of protein coming from bread. And then on the milk, each cup of milk contains 9 grams of protein, so 9y. We need at least, mathematically, that's greater than or equal to 90 grams of protein. Another thing this diet has to do is give us enough calories, specifically at least 2,700 calories. And so if I look at the calorie content, each slice of bread contains 60 calories, so 60x. Each cup of milk contains 90 calories, so plus 90y, and that needs to be at least 2,700. X and y are both physical variables, so x needs to be greater than or equal to 0, y needs to be greater than or equal to 0. And there's something else in this problem, this business about to guard against excess. The monks decide to restrict their combined daily diet to at most 100 slices of bread and 40 cups of milk. So they have some bizarre restriction that they're just going to say, hey, whatever else happens, we're not going to eat any more than 100 slices of bread, and we're not going to drink any more than 40 cups of milk. So x less than or equal to 100, y less than or equal to 40. Let's check out a graph of the feasible region here. All right, we have multiple things to consider now. There are 1, 2, 3, 4, 5, 6 constraints involved. The x greater than or equal to 0, y greater than or equal to 0 are just going to be the coordinate axes as before, but we really have 4 other lines now that need to be graphed. If I look at the first one, x plus 9y equals 90, the associated line, we'll find out that the x-intercept is 90 and that the y-intercept is 10. Let me redo that. I might want a slightly different scale. So 10 and 90. And the black is the line x plus 9y equals 90. All right, if we look at 60x plus 90y equals 2,700, we'll find out that, let's see, that y is 30 and that x is 45. So setting x equal to 0, setting y equal to 0 as we did before. And this is the line 60x plus 90y equals 2,700. Okay, let's go back and pick up the correct side. Notice that this is a greater than or equal to. So if I pick my origin and check it, 0 greater than or equal to 90 is not true. So in contrast to the examples that we've done so far, the origin is actually not on the correct side, and here we want to be in this direction of the black line above and to the right. For the red line, 60x plus 90y greater than or equal to 2,700. Again, the origin 0, 0 plugged into this inequality is not true, so it's on the wrong side, and we really want to go up and to the right there. Okay, the x greater than or equal to 0, y greater than or equal to 0 are just going to push us into the first quadrant. And now let's go here, x less than or equal to 100. Okay, if I graph the associated line x equals 100, that's actually a vertical line. So here out at x equals 100 is the vertical line x equals 100. And if I look at y equals 40, that's actually a horizontal line like this. And regarding direction there, well, x less than or equal to 100 is this direction to the left of. Those are x's that are smaller than 100. And for y, y less than or equal to 40 is down below this horizontal line. And now, if I look at the feasible region, it goes as follows. There's a region up here in the upper left-hand corner. Then it's bounded by all of these boundaries. And then here down in the lower right-hand corner, the boundary is actually just the x-axis for a little chunk here. So how about corner points? Well, there are a lot of them this time. There's 1, 2, 3, 4, 5, and 6. What are they? Let's list them one at a time. Say starting here, this is the point 0, 30. This is the point 0, 40. Now if I go over here, I can just read it off. The x-coordinate is 100 and the y-coordinate is 40. Down here in the lower corner is 100, 0. And next to it is 90, 0. And finally, there's only one that I can't just read off. So as before, solve the red and the black equations simultaneously, and you can find out that this last corner point is 36, 6. So 1, 2, 3, 4, 5, 6 corner points. That's more than we had before, maybe more than we like, but still the process is same methodology as before, just a little more work. Need to make a table of the coordinates and the cost function that we're trying to minimize. And our corner points now are 36, 6, 90, 0, 100, 0, 140, 0, 40, and 0.30. And now you take each of these, plug them into this function, and I'll just show the numerical results. It goes 132, 180, 200, 600, 400, and 300. Okay, remember this time what we were trying to do, minimize. So instead of looking for the largest number here, we want to look for the smallest number. It's right there. And so that's going to give us the answer to the question, and we can answer in an English sentence. Minimum cost diet is $132 by consuming, and let's bring the variable letters back to actual physical quantities. X was the number of slices of bread, and that turned out to be 36. 36 slices of bread and 6 cups of milk per day. End of problem. Thanks. Have a good day.